Welcome to an introduction to chemistry brought to you by Parkbench Tutors. For more information about Parkbench Tutors, just look us up on Facebook, or you can find us at parkbenchtutors.com. We're going to continue our study of the gas laws, and we'll start with Dalton's law for partial pressures, and that states that if you have a mixture of gases, then the total pressure is the sum of the partial pressures of the gases in the mixture. So if we want to write that down, the P total is equal to P1 plus P2 plus P3 and so on until you get Pn, which is the nth gas. So in an example of a mixture of gases, one gas has a pressure of 70 torr, gas B has a pressure 200 torr, gas C has a pressure of 500 torr. What's the total pressure exerted by the mixture? Well, we simply add these together. 70 torr plus 200 torr plus 500 torr gives 770 torr, so that's our total pressure. Now, when you're collecting gases, this is where you can apply Dalton's law for partial pressures, because if you collect a gas over water, then there are some water molecules present in the mixture as water vapour. So you have in fact got two gases there, the gas you're collecting and some water vapour. And the pressure exerted by the water vapour has to be subtracted to get the pressure of the actual gas being collected. So here's an example. If we have 400 mils of oxygen which have been collected over water at 23 degrees Celsius, 760 torr, and we know that the vapour pressure of water at 23 degrees Celsius is 21 torr, then what's the volume of the dry oxygen? In other words, how much oxygen have we actually got? Well, step one is to determine the pressure of the dry oxygen gas. We know that the total pressure is 760 torr, and that's made up of two partial pressures, that of oxygen and that of water. So if I subtract the partial pressure of water, then I've got the pressure of oxygen. So 760 minus 21 gives 739 torr. So 400 mils of oxygen at 739 torr. Okay, apply Boyle's law to that. In other words, P1V1 is equal to P2V2. We're looking for the volume V2. So V2 is P1 multiplied by V1 divided by P2, or 400 multiplied by 739 divided by 760. Right, the torrs cancel out and we're going to be left with millilitres, and the answer is 389 millilitres. So in other words, because there's a partial pressure for water, we haven't actually got 400 mils of oxygen, we've only got 389. Avogadro noted that if temperature and pressure remain constant, the ratios of the volumes of the reacting gases are small whole numbers. That's actually Gay-Lussac's law, and he took that statement and he then said, okay, if that's so, then equal volumes of different gases at the same temperature and pressure contain the same number of molecules. Okay, let's take hydrogen and oxygen combining to form water. Two volumes of hydrogen combine with one volume of oxygen and they give two volumes of water. Or hydrogen and chlorine combining to form hydrogen chloride. One volume of hydrogen combines with one volume of chlorine to give you two volumes of hydrogen chloride. Now, what Avogadro said was that a mole we know contains 6.022 times 10 to the power of 23 molecules. So at the same temperature and pressure, a mole of any gas has the same volume as any other gas. And the volume occupied by a mole of any gas at STP is 22.4 litres. That's called the molar volume. So 44 grams of CO2 occupies 22.4 litres, or 71.9 grams of chlorine, or 2.016 grams of hydrogen. So let's turn this into a problem. 2 litres of gas at STP has a mass of 3.23 grams, so what's the molar mass of the gas? We're converting grams per litre to grams per mole, so the conversion factor is 22.4 litres over a mole. So 3.23 divided by 2, and the answer to that multiplied by 22.4 comes to 36.2 grams per mole. Look at it another way. the mass in 1 litre is 3.23 divided by 2, so the mass in 22.4 litres is 3.23 times 22.4 over 2. Going to come to the same answer, 36.2 grams. That's of course 36.2 grams per mole. Right, second problem. At 40 degrees Celsius, 630 torr, the mass of 1382 millilitres of diethyl ether is 3.30 grams. So what's the molar mass of diethyl ether? Well, the first step is to apply the gas law. We are looking for the volume at STP, P1V1T2 over P2T1. Plug in our numbers, 630 torr times 1382 millilitres times 273 degrees Kelvin divided by 760 torr times 313 K, which comes to 999 millilitres. So we have to find our molar mass, which will be 3.30 times 22.4 divided by 0.999, which comes to 73.9 grams per mole. Now we go to the density of gases. Density is equal to mass over volume, so it's normally measured in grams per litre for gases, and the density at STP is the molar mass times 1 mole divided by 22.4 litres. So the molar mass is the density at STP multiplied by 22.4 litres. So calculate the density of chlorine at STP. Well, the molar mass of chlorine, Cl2, 2 times 35.45 is 70.90 grams per mole. So we've got to convert grams per mole to grams per litre. So we are going to divide by 22.4, so 70.90 divided by 22.4 gives 3.17 grams per litre. Now, the ideal gas law states that V is proportional to NT divided by P, where N is the number of moles, and V equals nRT divided by P, where R is the ideal gas constant. Can rewrite that as PV equals nRT. Okay, so if we want to value for R, the ideal gas constant, it will be PV divided by NT. A pressure of 1 atmosphere times 22.4 litres divided by 1 mole multiplied by 273 degrees Kelvin. We have a value for the ideal gas constant of 0.0821 litres per atmosphere, right, liter atmospheres per mole per degree Kelvin, which we can also write as liter atmospheres mole to the -1 K to the -1. Okay, let's do a problem based on that. What will be the pressure exerted by 0.4 moles of a gas in a 5 litre container at 17 degrees Celsius? We want the pressure. We know that PV equals nRT, so P must be equal to nRT divided by V. So P is equal to 0.4 moles, the ideal gas constant 0.0821, the temperature, which at 17, so it's 273 plus 17 is 290 degrees Kelvin, and we divide all that by the volume, which is 5 litres. And you can probably see that litres are going to cancel out, moles and moles -1 will cancel out, and degrees Kelvin and Kelvin to the -1 will cancel out, leaving you with an answer in atmospheres, and it comes to 1.90 atmospheres. Okay, we'll try another problem here. How many moles of oxygen gas are there in a 50 litre tank at 22 degrees Celsius if the pressure is 2,000 pounds per square inch? Note we've mixed up a few units here, so let's get this pressure into something reasonable. So we'll convert the pressure to atmosphere, and an atmosphere is 14.7 pounds per square inch. So if we divide 2000 by 14.7, we'll have a pressure of 136.1 atmospheres. Okay, now all we need to do, we start with our PV equals nRT. We're looking for N, the number of moles, so N will be equal to P times V divided by R times T. We'll plug in all those numbers now. N is equal to 136.1 atmospheres times the volume, 50 litres, divided by the gas constant 0.0821 multiplied by the temperature. So 22 plus 273 is 295 degrees Kelvin. So there are 281 moles of oxygen. That ends our session. Thank you for watching and listening. For more information about Park Bench Tutors, find us at parkbenchtutors.com or look us up on Facebook.